Okay. Yeah. 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 No, it's gonna be quite tricky.
So
That's perfect. Okay. So I go up. No. Yeah. Of course.
hello, everyone. Welcome to today's CAP seminar. Today we have with us Gabriel Pinto Morales. He is a geochemist specializing in meteoritics and cosmochemistry. He earned his bachelor's in geology from the Universidad Católica del Norte in Antofagasta, Chile, and his PhD in geosciences from the Université de Lorraine in Nancy, in France. His PhD research focused on the oxygen isotope signatures and recycling processes in the first solids produced in the early solar system. And currently, he is a postdoctoral researcher at the Université Libre de Bruxelles and Université de Bruxelles in Brussels, where he studies the distribution of highly siderophile elements and in the inner solar system and the accumulation and alteration of meteorites in hot in the Atacama and cold in the Antarctic deserts. In addition to his research, he serves to the subcommittee of the Extraterrestrial Materials Analysis Group and co-founded the Pelham Cura Meteorite Repository, which is the first facility in Chile to perform official meteorite classification. Thank you very much.
Thank you very much. So I don't know if you can hear me well. It's good? Perfect. So first of all, thank you for coming to the presentation. As with the introduction, I am a postdoctoral researcher working in the Université Libre de Bruxelles. And today I'm going to present our last expedition to Antarctica. It was in the season 2024-2025. But first, I would like to introduce you these pictures. That is basically the evolution of our solar system in a clockwise direction. It's an illustration sketch that we did in a book for outreach in Chile. So basically, as you can see here, we start 4,567 million years ago with the early condensate of the first solid in our solar system. So we have the solar nebula that really quickly passed to a protoplanetary disk when we have the accretion of the big planets and the asteroid. And also we have different collisions and events. And after we have the formation, for instance, of the moon with the protoplanet Theia. And subsequently, we have a lot of migration of asteroids from the inner to the outer solar system, etc. What is the most important thing is like we are here today with the structure of our solar system. With 4 terrestrial planets in the inner solar system, we have the main asteroid belt, and we have the 4 gigant planets and the Kuiper belt, and farther away we have the Oort cloud. Basically, how we know all this story that I am telling to you, it's thanks to the meteorites, okay? Meteorites are fragments of asteroid planets or moons that can arrive to our planet when they crossed in the orbit direction of to the sun, and they can felt in the surface of our planet, and after they can be accumulated in different regions that we're gonna see a little bit further. Mostly of the meteorites that we can find in our planet comes from asteroid sources. So for instance, thanks to the different meteorites, we can create a schematic classification of all these different asteroids. In one side, we have the undifferentiated bodies, or bodies that were never totally melted. So they preserve the early condensate, the first solid produced in the early solar system. And also, they have a lot of organic material. Like, for instance, we have the carbonaceous meteorite here that is really interesting for prebiotic studies to analyze the organic compounds and how was probably the origin of our life in our planet. But we don't just have the carbonaceous meteorite, we also have other classification of these chondrites that show us different objects that were produced in the evolution of our solar system. So in the other side, we have the differentiated meteorites. The differentiation is a process that happens when it's melted and we have a segregation of the elements according to the affinities, the geochemical affinities. For instance, we're going to have in the core most of the siderophile and chalcophile elements, and after we're going to have in the surface an accumulation of the lithophile elements. So for instance, we know about this process thanks to all the different meteorites that we have found. we have found. For instance, we have the iron meteorites that represent probably the core of other planets or protoplanets that were already differentiated and they were destroyed in different debris. And we have access to this formation process thanks to the meteorites. Also, we have the stony iron meteorite that, like the palisade, the beautiful metallic meteorite that have insert olivine crystals that today we think that they are coming from the boundary of the iron and the silicate mantle. And in the other side, we have the echondrites. And the echondrites, it's basically all the rocks that come from the surface of other planetary bodies. We have samples from the moon, we have samples from Mars, and we have samples as well from Vesta, that is the Hertz meteorites. So what is important about all this schematic classification of meteorites is the fact that not all of them went through the same process. So this kind of different characteristic and physicochemical properties and petrographic distribution, chemical composition, and isotopic composition tell us how were the production of the bodies in our solar system. So there's two ways to find meteorites. The first one, it's just try to following the shooting star. And following this shooting star, we can use a camera network and after calculate the triangulation of where this extraterrestrial material fell and just go to looking for it. There are only 2% of the meteorite in our collection has been recovered in this way. In the other hand, we can find the meteorites just by chance. Like for instance, here I like to talk about this case is the Hova meteorite. That is the biggest meteorite in our collection. It's over 60 tons. And it was found only by chance in Namibia by one guy that bought this land and he was expecting to build something and he found a huge iron meteorite in the sun. In the other hand, you can work a little bit hard and select different areas to perform systematic search for meteorites. And this is really important because we have that the meteorites don't fall in any position because they like to fall in areas of the planet. They are fall everywhere, anywhere, and they are accumulated. That is the tricky part of the meteorites. And the meteorites are accumulated in desert. They can be cold or they can be hot desert, but they are better preserved because they don't have erosive process. The biodiversity is really, really low, so it's more easy to find a meteorite in the desert than in a forest when you need to move all the plants, etc. So for that reason, we always select hot. In this case, you can see a picture of the Atacama Desert looking for meteorite. This is Kevin, the one that is doing some analysis here as well. And we also select the Antarctica, okay? And today we're gonna focus in the Antarctica expedition looking for meteorites. So what is important about Antarctica? It's extremely dry and it's extremely pristine. We don't have any big city. We don't have any native people that were living there. We don't have much civilization in Antarctica. So most of the areas are really not well explored. And in the case of meteoritics, it's really, really relevant because most of the samples in our collection are coming from Antarctica. 60% of the meteorite that we have are from the white continent. So all these meteorites also show less terrestrial alteration when we compare with meteorites, for instance, from the Sahara or from the Atacama Desert. They have less contamination, so they are so pristine and they are trying to help us to understand the formation of the solar system. Of course, we need that the sample is really pristine because we have overprint of other process, and the terrestrial alteration is one of them that can make us confused when we try to interpret the data. So another thing that is really important here, well, you can see the map of Antarctica. We have the division between Eastern Antarctica and the Western Antarctica. And we have also the Transantarctic Mountains that are going to be important in the next slide because a lot of meteorites have been found there. So what happens in Antarctica, the difference with, for instance, hot desert, when we go for looking meteorites in hot desert, most of the meteorites, they just fell and they land in the surface and they stay there per million or hundreds of thousands of years. In the case of Antarctica, it's quite different because we have an accumulation of the extraterrestrial material and the terrestrial material as well, thanks to the ice flow. So we have, here the sketch is perfect. So we have that the extraterrestrial material fell into the snow in the accumulation area, and after this extraterrestrial sample is transported in the ice sheet, and when we are transporting all this ice sheet by a gravitational force, they are totally pushing towards the barrier of the continent to the ocean, they can find an obstacle, they can find a barrier. And this barrier can be an emerger barrier or a submerger barrier, but basically what does, the ice is pushing towards the surface, it's a slow down, a push toward the surface, all the rocks or fragments that has been transported in the ice flow. So basically we have a push of all this extraterrestrial material up, and after we also need to have like the ablation process, the wind for instance, produce some sublimation of this area, and we can exhumate all these meteorites. So basically how we found meteorites in Antarctica, we go to specific areas when we have a lot of accumulation of rocks, and we start to identify this extraterrestrial material. And it's different how we do in the hot deserts. So this means that not all Antarctica is full of meteorites. I mean, if we go to Antarctica and we go to an area full of snow, we will never gonna find a meteorite because they are accumulated in a specific zone. So here there is a diagram of all the different dense collection area in Antarctica associated with meteorite find. So as you can see here, the Transantarctic Mountains, there have been a lot of expedition, mostly for the ANSMET, that is the expedition from NASA. And we have also in the Eastern Antarctica a few areas that has been really, really abundant of meteorites. For instance, Yamato, it was explored for many years for the Japanese expedition, and most of the meteorites that coming from Antarctica are coming from Yamato. So now, as you know, not all the blue ice can have meteorite accumulation. And what is the most important thing is the fact that perform an expedition in Antarctica, it's not cheap at all. It's really expensive and it's a lot of work. So we cannot just go to explore all the blue ice to try to find meteorites. So we use machine learning process. That it's an approach that has been proposed since a few years ago. Like for instance, here there is papers from 2020 and 2022. And here you can see in the diagram the probability of find meteorites along different regions in Antarctica. So as you can see, the red probability is high probability, but most of this model, they are good, they help us, and we can use it as an argument to go to looking for meteorites, but they are based on characteristic of the ice, for instance, the movement of the ice, the thickness of the ice, the temperature of the surface, the distance from the outcrops. Like the machine learning is still on a model that depends on the parameters that we put in. So basically, we're gonna go directly to the Eastern Antarctica. Here we have the Yamato ice field, and here we have the Sohr-Rondaine Mountains. And here in this tiny isolated mountain chain is the Belgica Mountains, okay? So in the Belgica Mountains, it has been already 3 expeditions. The first one, it was in 1957 and 1958, that it was a Belgian expedition. For that reason, they put Belgica Mountains. And after we have 2 expeditions by the NIPR, that is the National Institute of Polar Research, that is a Japanese institution. And they went to look into do the geological map of the area, but they also found 5 meteorites. They were not looking for meteorites, they just find 5 meteorites. And after we have the 28 meteorites in a second expedition performed also by the Japanese in 1998. So what is important here, for instance, you can see in the diagram is the Belgica Mountain, and these are the meteorites that were found by the Japanese expeditions. And here you have the Belgica Mountain as well, but with the model of the machine learning showing all the different places that we can have also accumulation of meteorites. So basically, we base our expedition in this machine learning process to try to explore these areas that are remarked by red. So something that is important as well is the age of these meteorites. Okay, these meteorites are quite old, and in the case of the Belgica Mountain, they have 5 datation by cosmic ray exposition, and this cosmic ray exposition gives us age between 70 to 240 thousand of years. So how start this adventure? We start in Brussels, of course, with some fries, chocolate, waffle, and some beers. It's really, really good. I really advise you to go for it. We travel from Brussels to Cape Town in South Africa. We stay there a few days. And after from Cape Town in South Africa, we travel to Antarctica using the Perseus plane. And it was really funny because you need to go to the airport, and in the airport you have all the flights that are going, I don't know, to London, to Amsterdam, and you have the flight going to Antarctica. So it was really, really funny. And when we arrived to Antarctica in this plane, that well, there were tourists as well. There were Chinese tourists, a lot of Chinese tourists that they were going to Antarctica for 1 week. And we are right here to the blue ice landing area. And after we drive with this nice wheels truck to the Belgian station that was around 3 hours from the area of the landing area. So here I'm gonna show you a little bit the adventures that we had to go to the Belgica Mountains. So as you can see here is the same map that before. We have the Yamato Mountains here. We have the Belgica, the main objective of our mission. We have here the Princess Elizabeth Station. This is the Belgian station in Antarctica where we arrive and we stay there for a few days. And from the Princess Elizabeth Station to the Belgica Mountains is around 350 kilometers. It's maybe not so far if you think like in Europe distance, it's like 3 hours, 4 hours driving. But here in Antarctica, it was quite challenging to arrive there. So first of all, we arrived to the Princess Elizabeth Station. As you can see here, we have some training to drive the skidoo. We have some training of first aid. We have some training to rescue people from the crevasses, because remember, Antarctica, it's full of crevasses. That is the difference of the velocity in the glacier flow between the center and the border. It's like the river, exactly like the river. We have that the part in the inner movement of the glacier is faster than in the border. So we produce some fractures, really, really deep fractures. And these fractures can be really dangerous. So it's something that we need to learn. Someone fell with harness, of course, and after you need to learn how to rescue this person that fell if we have some problems in the field work. So it was really nice. We learned a lot. We stayed 1 week and a half. And after we start the trip, we start the mission. And for the mission, we decide to use containers. We have kitchen containers. We have bed containers that we were, all of us sleeping in the same container. We have like different beds. And basically, we were here, as you can see in the picture, we have the containers, we have the kitchen, and we were pulling by a prino. This is the prino that was cleaning the snow first. And after, well, it was also pulling over all the container. It was quite heavy, and the maximum speed was like 15, 20 kilometers per hour. So it was really, really slow. For this route, we did around 3 to 4 days. We stopped in Balkan to do some collection of meteorites here in this area. And after we were ready to start to cross to the Belgica Mountain. But as you can see here, it's really, really isolated. And all this white desert that we need to cross, it was full of huge crevasses. Like for instance, you can see here in this picture, we were in the container there inside. And when the container just crossed there, you just see like a layer of snow. But underneath the snow layer, you can find these fractures, huge fractures. And we were in the container, and well, it was really close to fall the full container into it. But lucky us that nothing happened. But yeah, we lost one of the sledge that was in the roof of the container. So at that point, the lead of the expedition, that was not a scientist, was the director of the Princess Elizabeth Station. He told us, okay, guys, I think it's going to be really complicated to cross to the Belgica Mountain with this method that we are proposing. So he told us that he have another plan. There were another big project called the Ring project, studying the climate change in Antarctica and everything. And they come to us and they give us, or well, they don't give us, they help us to move the stuff from the camping close to the Balkan Mountain to the Belgica Mountains. So they arrive with 2 helicopters, and they arrive as well with a flight. So here, for instance, you can see one of the videos of the helicopter that, I mean, for looking meteorites, we need the skidoo, and also to explore the new regions that are quite far apart of the area of the camping. We need the skidoo. So basically, we transport 4, 5 skidoo, because we were 4 researchers and we were 2 guides, specialists. They were doctor, and they were also with so many years of experience in Antarctica. So basically, I was feeling like in a James Bond movie, because it was just crazy. And the helicopter just arriving, and at some point we were thinking maybe there's no mission anymore. Maybe we need to come back to Brussels. And the guy gave us this idea, and they helped us a lot to move all the stuff. So basically, after we arrived to the Belgica Mountains, we set up the camping. We are not sleeping anymore in containers. Now we are sleeping in tents. And we adapt a lot the mission. It's how it happened in Antarctica. You never know what can happen, so you just need to be ready and prepare to adapt yourself to the conditions. So basically, we have everyone on a tent. This is our nice toilet tent that at the end of the mission, it was like really destroyed because the wind, it was really strong. So we didn't have a toilet tent anymore. And this is the kitchen. We were taking dinner, breakfast in the morning every day. And this was like the planification tent when we have the maps, we have the radios, because every day we need to charge the radios, and we start with the radio and we communicate with the radio, because we were like in different skidoo, driving apart, close, but still too far to listen to each other. And also the wind, it was really, really strong. So once we arrive there, here we start right away to looking for some meteorites. So for instance, here you have one of the video when we found one of the sample. Basically, what we do is we separate each other. We were 4 different skidoos. And in these skidoos, we were separated 15 meters, more or less. And the first one, the one in the middle, we have like a B position. And this B position, we were looking for meteorites around. And when someone finds a meteorite, everyone stop. You stop your skidoo, your snowmobile. You stop your snowmobile. You go just down. You see the sample. For instance, here you can see the meteorite there. It's like there is a lot of rock. There is not only meteorite. There is a lot of terrestrial rock. So you need to take care. You need to know how to recognize meteorite in the blue ice. And basically, what we do is we write the name. We write the name of the person that found the meteorite, the date. And at the end, we write the number of the meteorite that we have found in the same day. So we take a picture with the scale. Normally, we use the marker. And for collected, we don't touch them. So we use the plastic bag. And with the plastic bag, we try to push the sample inside. Sometimes we have some problems. So you need to crash a little bit the ice with a hammer, or sometimes just like hit a little bit with the marker, and you can move the meteorite, basically. But as you can see, all this area were like, this was the first day. We were just starting, and we were really lucky to find some of them here. But it was huge, and it was among us. It was just too impressive landscape and blue ice field. So yeah, and it seems warm, but it was pretty cold. So here we have some of the samples that we found. I'm gonna start from the right side. So here is an apalacite. I don't know if you remember the apalacite that I was telling. It's this boundary between the core and the mantle. So we were really happy because it's a really weird meteorite. There has been only 35 meteorites with this classification found in Antarctica. So we were super happy when we found several pieces of this apalacite. We found a lot of meteorite that they were sink into the ice. And this is really interesting because at some point, Most of the minerals in meteorite are mafic minerals, are olivine, or sometimes you also have the fusion crust, that is when this extraterrestrial material crosses the atmosphere and you melt the surface. And what produces this is like absorb the heating of the sun. And after you start to increase the temperature of the sample, you melt the ice around the sample and the meteorites start to sink into the ice. So we found a lot of meteorites that they were really sink, and also terrestrial rock. We found a lot of amphibolite, for instance, or gneiss, the mafic part of the gneiss that were totally sink into the ice. We have some nice samples here, for instance. You have like a fusion crust around, so it's preserved quite well, but inside it looks really, really rusty. We also found a carbonaceous chondrite that we sampling with aluminum foil because, well, as you know, the carbonaceous chondrite are full of organic material, and this was really matrix rich, and most of the carbonaceous chondrite that are matrix rich, they have a lot of organic compounds that can be produced in the parent body, in the asteroid, not here in our planet. And here there is like a tiny game. I don't know if you can recognize the meteorite here, but basically we found a lot of meteorite in this way. They were just hanging around with some terrestrial rocks with the friends from the Earth. So for instance, here you have like some terrestrial rock, and here we have a tiny meteorite that was just hiding with the other samples. So most of the meteorites that we collected, they were accumulated in the other side of the ice flow movement, which is quite logical. We have the katabatic wind. This is the direction that shows the north. So it's moving in this direction, the glacier as well, together with the katabatic wind. So probably the ice flow is doing this. It's slowing down by the mountain range. And after it's turned around, and when turned around, it's slowing down and probably it's accumulated all the meteorites in this region. For instance, here we have a zoom of the area. And in a zoom of the area, you can see that all the meteorites are accumulated almost in a line, because we have probably a submerger barrier here. We have this mountain, but this mountain probably is continuous below the ice sheet. So probably the ice flow is slowing down and pushing up towards the surface all the terrestrial rock and the meteorites there, which is interesting. And we found in the Belgica Mountains is the fact that we have a secondary accumulation of meteorite or distribution of meteorite that is associated with the wind direction. So when you go outside of the Belgica Mountain, the camping, it was there, so we were protected from the wind, but there the wind, it was just insane. It was really, really complicated to just traverse the mountain change because the wind, it was really strong, it was really cold. We went like 3 or 4 times there, and it was like, it was the hell. The real hell of Dante Inferno. It was like a cold hell. Really, I remember so much that book. So for instance, you can see here the distribution of the meteorites. Most of the fragments were accumulated in this area. And here, for instance, we found biggest meteorite around 300 or 600 grams, but they were only explored by the guides because they went there, they explored the area, and they said it's too dangerous for scientists. So we're going to go another day. We're going to look for meteorites because you teach us how to look for meteorites, but you cannot go there. So we didn't have access to this area, and they found the biggest ones. But, and it's interesting as well because the Japanese, they didn't arrive there because it's an area full of crevasses that it's really easy to fall down into the fractures. So here you can see a diagram of the probability density function. We have the mass in the x-axis, and in the y-axis, we have the relative frequency and the probability density. We have 115 meteorites, potential meteorites, let's say. It's around 2.3 kilograms of extraterrestrial material, and most of them were really tiny. Like if you can see here, the mean or the average of the sample distribution, it's around 20 grams. So it's not so big samples. We found a lot of 9 grams or 6 grams. And basically what is interesting as well is the fact to see by person. So I did this same distribution, the probability density function of the samples that have been found by every one of the people in the expedition. And basically, yeah, Hamed, is the HP, he found the biggest one somehow. And yeah, the mean is a little bit bigger compared to the rest, but we are inside of the error of everyone. So it's we hope that we didn't lose the really tiny ones, because yeah, we were really at some point we stopped with the skidoo, especially in this area of the accumulation of meteorite, and we just start to walk. And walking, we clean all the area of meteorites. Here is the magnetic susceptibility of the meteorite. The magnetic susceptibility, it's basically we create a field, like magnetic field, artificial magnetic field with an instrument, and the magnetic field interacts with the metal abundance in the meteorite. So with the magnetic field, we can know how much metal this extraterrestrial material have, or we can differentiate if it's a terrestrial rock from an extraterrestrial rock. So for instance, there is different diagrams that show the range of the magnetic susceptibility of the meteorite. This magnetic susceptibility is expressed in log of Xi, and here we have the mass in a logarithmic scale. So as you can see, most of the meteorite, they are not too heavy, but we have few of them that are quite big, around 600, 300. And here, the stony iron meteorite is the palisade one. So as you can see, we don't find only one palisade iron meteorite. We find several of them. And also, we found a lot of ordinary chondrite. And here is important because ordinary chondrite is not because they are not relevant, but they are the most common meteorites that we can find in the surface of Earth. So the ordinary chondrite have subclassification that is according to the abundance of metal. So we have H, we have like most of them are H probably. We have some L and we have some LL. And otherwise we have some echondrites that are meteorites that come from the crust of other planets. And these echondrites, yeah, probably we have some terrestrial rocks as well, in this group. And the minimum is 3, and below 3 for sure it's terrestrial rocks. So here probably we have some amphibolites or gneiss or stuff that we were just picking out, saying like, maybe it's a meteorite. And at the end, when we did the analysis, it's not a meteorite, but it happens. So what is the ongoing work right now? It's to do the classification, the official classification of this meteorite. Basically, in meteoritics, you need to perform the classification of the meteorites to write a paper or to study this sample. And what we need to do is prepare a fixed section, and after analyze the chemistry and the petrography of the meteorite, the olivines and the pyroxene normally. And for the more weird and the carbonaceous of the metallic meteorite, we need to have bulk oxygen isotopic analysis, or we can have other isotopic composition, but they always ask you for more precise analysis to do the classification of these rare meteorites. And at the end, we submit to the Meteoritical Society. In the Meteoritical Society, they check the description that you did about the meteorite, and they said, okay, this is approved. And after the meteorite have a name, and this name it's open to the meteoritical community. So other extraterrestrial material or other samples that are also collected in the field, it was the micrometeorite. So as you can see, we select different areas to extract sand. Micrometeorite, it's basically extraterrestrial material that are minor to 2 millimeters, like smaller than 2 millimeters. So here in the picture, you can see the scale that is 500 microns. And the 500 microns, you can see a lot of spherules melts. You can see all these tiny black particles are micrometeorite that are produced by the accumulation of this extraterrestrial material. Sometimes they are the parts of the fragmentation of a big meteorite that is just distributed in the atmosphere, and after they just fell down into the surface. So what is important about this accumulation of micrometeorites, it's understand the flux of extraterrestrial material in these regions of Antarctica. So basically, we use sedimentary traps to sampling these sediments. So we have here in the picture, you can see the exhumation of the rock here of the mountain. We have a sedimentary trap that is a fracture in the rock that is open. And this fracture in the rock, it's accumulated all the dust that is falling down, but also it's accumulated extraterrestrial material. And what we do, we take a sample of this rock, we do cosmogenic nuclides to know how long this rock has been exhumated to the surface, and we calculate how much micrometeorite we have in this fracture, and we can estimate how much abundance of extraterrestrial material has been in this range of time. So this method, we use it in 8 different points of the Belgica Mountains, and this helps us to understand if we have a variation in the extraterrestrial material flux that is coming from different parent body. For instance, we can have more abundance of ordinary chondrite, we can have more abundance of carbonaceous chondrite, and we understand this in a geological scale. And the last one, the last part of the expedition that we sample some soils, and why I am here in the cave is to do some analysis of sediments that we extracted from different moraines. Here, for instance, in the left, you have the map with all the different sediments areas that we sampled. And all this sediment has been collected like in a sterilized tube and everything. And we're gonna also analyze some meteorites to try to know if the distribution of lipid compounds and the isotopic composition of the lipid compounds are similar to the one that we found in meteorites, and try to estimate if we have a potential microbial colonization of the samples in the area. Here, for instance, we have already done this kind of studies with Daniel Carrizo, that is my main collaborator, and Laura Sanchez Garcia as well, and Victor Parro and other people from the lab. We have studied the distribution of lipids in meteorites from the Atacama Desert compared to the soils. That is a recent paper that was published beginning of this year. And now the idea is try to understand or use a similar method to see how it's producing the accumulation of if we have some microorganisms. Because in this case, most of the meteorites were found in the ice, they were not found in the soil. So probably the microorganisms or the organic compounds, terrestrial organic compounds, they need to transport to the meteorites. And for that reason, we select different meteorites closer to the outcrops, closer to the mountains, and farther away to the mountains to see an internal variation of the lipid distribution of the meteorite as well. So even in Antarctica, we can see some water. Some days it was really, really warm. We were close to -2, -1. So we have some raining water around. So this is one of the areas that I sampled some sediments. And as you can see, we have a tiny waterfall, just a tiny river that it was just running from the topographic areas, the high topographic areas to the bottom. And we found a lot of water in Antarctica, which is, I was not expecting to find that amount of water in Antarctica. So with that, I just would like to say thank you for your attention. And also thank you for your really warm welcome here in Spain. I has been enjoying, it has been having a really good time here these days. Thank you.
Thank you so much for the great talk, Gabriel. We have time for several questions, so.
Thank you, Gabriel. I have a stupid question. Is more about when you talk about the accumulation areas.
Yeah.
It is accumulation is in terms of where they fall more for whatever reason, or where they accumulate because of the topography, the winds, and so on, that you call them accumulation areas.
Yes, basically we say the accumulation area, dense accumulation area for meteorite recovery, it's areas that, they are just preserved. In the case of Antarctica, what happened is the ice dynamics produce an accumulation of this extraterrestrial sample in specific areas. In the case of the Atacama Desert, it's quite different because we try to understand different aspects as how dry it is, the slope as well. For instance, we will never find a high accumulation of meteorite in the hill of a mountain. We need to have a quite flat flat area. And the sediments as well is really important. We need to have an deflation surface. So when you have an deflation surface, you clean all the fine-grained dust and you exhumate this meteorite. And this is in both. It's in the Atacama Desert. We need a lot of wind to clean the area and to accumulate the meteorites. And in Antarctica, it's the same. If we have the barrier, as I was showing in the sketch, we have the barrier that the ice flow, it's accumulated the meteorite here. If we have a lot of accumulation of snow or the accumulation is larger than the ablation process, we will never find meteorites there.
And in terms of the whole globe, are there specific areas where they are more abundant because they fall more, or is it is just that the most desertic areas, as you previously said, it's easier to be preserved and found?
Yes,
but they could be everywhere.
Exactly. It's exactly as you say, they can fall everywhere around the planet. There is not a specific, there were some studies with the shooting star. They were trying to estimate if there is a region on Earth that we have more extraterrestrial material that is falling into the planet, but it's not the case. And now we just use areas that we know that they're gonna have accumulation of meteorite because they are preserved. Like if we talk about age of meteorites in the Earth, in the Atacama Desert, they have been found meteorites up to 2 million of years of antiquity, and in Antarctica as well. So it means that this extraterrestrial material just fell there and it's stayed there like that for 2 million years in the surface. So it's just accumulation of extraterrestrial material. And in the other case, now, for instance, there is a huge camera network here in Europe that is FRIPON. And FRIPON, it's trying to detect all this shooting star to try to recover the meteorite. And sometimes even after 1 week, for instance, it fell one which can be in 2021 in UK. And this meteorite, after 1 week, it have already evaporites. It have calcium sulfate, it have carbonates. So if meteorite fell in a really rainy area or in a forest or in the ocean, for instance, I mean, we have access to micrometeorites thanks to the drilling in the ocean that we can collect some extraterrestrial particles similar to the case of the micrometeorite that I was showing. But yeah, we still don't fully understand, or we cannot collect the meteorite that fell in the ocean because probably it's gonna be really, really hard to reach the bottom. And also it needs to be really quick because the ocean is gonna destroy it. We need to remember that all this extraterrestrial material were produced in a totally different physical-chemical condition, temperature, etc. So they arrive to Earth and the atmospheric condition, they start to feel weird and they start to oxidate. The mineral phases start to change and they can be deteriorated quite fast.
Thank you.
Thank you.
Thank you very much for your nice talk.
Thank you.
I have two related questions. The first one is, if you can give us some more information about how to apply machine learning to this subject. And the second, very related one, would be if you think that it really made a difference in comparison to other classical methods of finding where to go and find, or even if you just, because I'm a total dummy on this subject, if you just went to any part of the Antarctica, would you find something there? So
okay.
Are there meteorites everywhere?
Yes. Well, let's start for the second and after we move to the first one. No, the answer is no. If, for instance, in the Belgica station, the Princess Elizabeth station, it's in an area that is full of snow and you have some patches of blue ice, but the dynamics of the ice, the wind as well, and the temperatures are not the same. So something that is important to remark is that every dense collection area of meteorite recovery in Antarctica, even if they have similar factors that produce the trap of meteorite or the accumulation of meteorite, the different factors have different levels of integrity in each individual zone. So it means that probably in some of the areas, the wind is more strong and it affects more to the accumulation of meteorite than the dynamics of the ice. So this is quite complex, and that is why we're gonna come back to the first question about the machine learning. It's so tricky to try to model the accumulation of the meteorite in Antarctica. It's because also you have a local condition, and the local condition, I will say it, the geology, I will say the number of crevasses. For instance, one of the, maybe I can show you this diagram, for instance. This diagram is showing the machine learning process with the meteorite that we found. So as you can see, this is the machine learning, and this is the meteorite. It's like just in the border outside of the machine learning process. So it's, even if it's really interesting and it can help us to understand where we can find, at the end, when you are in the field work, you just don't see it. And for instance, we went to different areas. We went to the top, and in the top, something that is not added in the machine learning process is the crevasses. It was a blue ice. It was really beautiful. Probably the temperature, the thickness, or all the parameters that they were using, it was okay, but it was full of crevasses. So even if a meteorite is accumulated, the crevasses, they're gonna fall down several meters in deep. So at some point, of course, we didn't find anything. We were just worried about to fall in a crevasse. So it was not the moment to looking for meteorites, but there are different parameters and aspects that I think today they are still under study to try to fully, I will not say fully, but try to be closer to the natural process that produces the accumulation of the meteorite in these regions.
But you're optimistic with machine learning in this case.
Yes, of machine learning, yeah. Like for instance, this model of the machine learning use a lot of ice properties, but yeah, they didn't take into account the crevasses, for instance, that it's something that is obvious because, I mean, you have a lot of fractures that you will not find any meteorite because it's full of fractures. So tiny details sometimes that can affect a lot the accumulation of the meteorite in these regions is this aspect that probably you need to improve in the machine learning process.
Okay.
Hi, thank you very much for the very nice talk. So I have a question, but before going to that, a follow-up about this. So you have shown here in this slide,
okay,
yes. Yeah, that you have found meteorites in a region which is close, but not within the one predicted. So are you thinking about use the results you are getting after the expedition to improve the learning of the machine learning to better predict places for next expeditions?
Yes.
So including new parameters or the things that you have learned in situ there?
Yeah. Yes. So basically, we are working in collaboration with Verónica Tollenar, that is the postdoc right now that did this machine learning model, and it's really interesting because they were in Antarctica as well, not in the Belgica Mountains. They went to another region, but we spent a lot of time together in the station, in the Belgian station. So we talk a lot about her model and the different parameters. And it's nice that this expedition, even if they have different objectives because they are looking for the oldest blue ice in Antarctica, and we are looking for meteorites, we share always the connection. And for instance, now they are using the datation of the meteorites to have the minimum age of the ice. Because for instance, if we found a meteorite in this blue ice and they are looking for the oldest ice, we take the meteorite, we do cosmogenic ray exposition, that it has been exhumated to the surface. And after we have an age of this meteorite exposed to the surface, and we have an age, minimum age of the ice, because the ice need to become common with the meteorite, and they can estimate which areas in Antarctica have the oldest ice. So it's like, I have the feeling that now it doesn't work if we stayed in our own disciplines, working in our own analysis. Every day it's becoming more the interdisciplinary aspects with analysis of different point of view and with different professionals to try to understand a complex process. And that is exactly coming back to your question. We are also sharing a lot of information. And of course, I mean, she already knows that we didn't find any meteor with the model, but at the end, when you apply to the project, you cannot apply to the project in the air, and you need to have a background or an argue to say, I'm gonna go to the Belgian Mountains because boom, the machine learning. So at some point, it helps. It helps to find the real answer, and it helps to after improve with the information that we collected in the field.
Okay, and the other question was about the age of the meteorites.
Yes.
So is there any gradient of ages according to the different places? So in the Belgica Mountains,
Yeah,
the
it's a really
ages
good
are
question.
different to those in Yamato, for instance?
Yes. It's a really good question, in fact. Really good question, because that information also give us the dynamics of the ice.
Exactly. Yeah,
because probably, or the area of the accumulation of this meteorite. But at some point, we have that most of the meteorite here, as as I show in one of the slides, the age of the meteorite in Yamato, it was around 50 to 240, but there were only 5 with the cosmogenic ray datation. But in Yamato, they have been in Groves Mountains, they found 2 million years old meteorite. So they have a different range, different age, and different distribution, but it's still not fully understood because, for instance, something that we in the meteoritical community is really well known is that the meteorites from Antarctica, they are better preserved. They are much better preserved than the meteorites in the Atacama Desert. And now I am working with meteorites. I worked during my PhD with meteorites from the Atacama Desert, and now I am working with meteorites from Antarctica. And for me, they are rusty, like they are even worse than the meteorite in the Atacama Desert. So at some point, I think there is still a lot of things to understand about it, because it's not the same if you find a meteorite close to a moraine that you can have some liquid water associated, that in the blue ice inland. So, and it's not the same if you find the meteorite close to the coast or if you find the meteorite really in the center of the continent. So there is a small aspect that we say the Antarctic meteorite are the more pristine. It's on a full continent. It's too big. Probably there are regions that they are more pristine, and these regions are exactly associated with what you say, the age of the meteorite. Probably the oldest meteorite in this dense collection area are associated with better preservation of this extraterrestrial material. But yeah, it's a really good question.
Thank you.
Any other questions? Is there anything on Zoom? No? Okay, then thank you so much, Gabriel.
Thank you so much.